Hello, this is Jonathan Templin from Clemson University, and I am back with another lecture, this time matrix algebra and the multivariate normal distribution. Fun topics, so let's dive in. In this lecture, we're going to talk about, it's sort of a two-part lecture. In the first part of it, we're going to talk about an introduction to matrix algebra. So we'll be covering things like definitions of what a scalar, a vector, or a matrix is. We'll talk a little bit about basic matrix operations and a little advanced matrix operations. And we'll see how this is embedded in R as we go forward as well. But why? Why would I want to tell you about matrix algebra? Well, turns out if you go a little bit further in statistics past linear models, you will quickly encounter matrix formulas, formulae with matrices very quickly. So, for example, let's imagine you're interested in analyzing some repeated measures data, but things don't quite go as planned. And I just grabbed a user guide from Proc Mixed. And this, let me tell you, in my training and my history, I used to use Proc Mixed for mixed effects models, multi-level models. And I would go to this user guide as I was learning them and think, what the heck am I looking at here? But basically, it's this. This is a linear model, but it's written very concisely through matrices. And then when you get a little bit further, this is a likelihood function right here for maximum likelihood using multivariate normal. These are all matrices as well. And of course, the residual maximum likelihood, of course, it's right there. Um, the point I'm trying to make here is matrix algebra is something that is not often taught a lot about, but a little bit of knowledge of it will help you be able to digest what's going on in papers or technical manuals for how to do statistics. So nearly all multivariate statistical techniques get described with matrix algebra. Right? When new methods are developed, the first published work typically involves something with matrices because it makes the writing much more concise. Right? We can quickly chunk formulas into smaller sets. So, for instance, these are two very classic matrix formulas that we see in statistics. The first, X transpose X inverse X transpose Y. This is the formula for ordinary least squares estimates in linear models. In fact, that is how, well, a version of that is how computationally linear models are estimated. So when you use the LM function in R behind the scenes, it's taking this matrix product and providing you estimates. There's no iteration to it. It's one closed form. This other matrix product, lambda phi lambda transpose plus psi, that is the formula for what a factor analysis model says a covariance matrix should look like. So this shows up almost all the time in in confirmatory factor analysis and structural equation modeling. So it's another important matrix product as well. The other thing about matrix algebra, it's a great way to get out of boring conversations and other awkward moments. So if you're at a bar or a party and someone comes up to you and you don't really want to talk to them, just say, yeah, I'm working on some matrix algebra. Cut that conversation down real quickly. But let's start with a few definitions. This is from dictionary.com. A matrix is a rectangular array of numeric or algebraic quantities subject to mathematical operations. So let's focus here a little bit about rectangular array. It's a box. It's got numbers in it. You've seen them before. In fact, when you are in R and you click on the environment tab, you want to see a data frame, pops up a display of your data. Maybe there are observations across the rows and variables across the columns. That is a matrix. It's a way of storing data. Um, it's also a substrate on or within which a fungus grows. So that's more of the biological definition of a matrix. We're not going to be dealing with matrices. In fact, the nice thing about using a computer is the decay or the growth of fungus doesn't quite happen. At least not unless you put your computer somewhere that it probably shouldn't be. All right, that's a matrix. It's a box for storing data. It's a way of thinking about it. Algebra is a branch of mathematics in which symbols, usually letters of the alphabet, represent numbers or members of a specified set and are used to represent quantities and to express general relationships that hold for all members of the set. Blah, blah, blah. I remember being in algebra thinking, why do I care about this? This is where we are able to go back and say, okay, for all the times we have real data, we can plug in our data into X, we can plug our outcome variable into Y, and this will give us our result. Right? That is substituting X for your data. But the more important part of algebra is that a set, so this group of numbers, together with a pair of binary operations defined on the set. Right? So the operations themselves are things that we're used to. Like how do we define what addition is or subtraction is? Where we think about don't think about this much when it comes to regular numbers that we've dealt with, but in matrix algebra we have to think a little bit more about it because we're talking about adding boxes of numbers together or multiplying boxes of numbers. That also includes things like the identity. So in regular numbers, the number one multiplied by any number is just that number itself, sometimes called the identity. We have an identity matrix as well. And those operations are commutative or associative. You've seen this before, whether we can, multiply within a product and so forth. So matrix, putting them together, a matrix is a way of storing numbers or data, and algebra are the different operations you can do on the matrices themselves. So then you can think about all the operations we do on numbers: addition, subtraction, taking a square, uh, quote unquote division. Division in matrices is a little bit different. But this is putting it together what matrix algebra is defined as. And so why do we want to learn it again? Apart from, being able to try to understand how things are working, it's very abstract. And in general, you're thinking, why do I need to take this in addition to statistics? I'd say that learning matrix algebra is important for understanding how statistical methods work. And when you learn that, you learn when to use them, when not to use them. It's also good for understanding what statistical methods means and good for reading and writing results from new statistical methods. Now, I don't think you're going to be a matrix algebra expert after this class, but I will tell you another story. When I was an undergraduate, I was given a task. Actually, it was a class task about emailing professors. If you wanted to go to grad school, find a professor, email them. So I emailed a few professors and I got a couple of responses. And part of my email, I had asked, what was a junior when I wrote this. So what classes should I take my senior year to best prepare me to go into statistics or quantitative psychology, which is really what I was trying to study. And both replies said, you should take a programming class and you should take a matrix algebra class. And sure enough, I did both of those my senior year. And matrix algebra, learning that made learning statistics much easier. So that's for if you want to get into statistics at a much more in-depth level. But I think for us and our purposes, we're going to see matrices in the things you're reading. This is a way to try to open those doors and understand what's happening in the analysis. So this is what I like to think about as the first lecture of learning the language of multivariate statistics. And we've been doing multivariate statistics for most of the semester, but this is really how the language of it works. So here's our data example. Let's imagine it's a really simple example today. I have two variables. I have SAT scores. I would pretend that these are SAT scores. They're generated randomly, simulated. But let's imagine they're SAT scores from the math and the verbal section of the SAT. For 1,000 students, you have our descriptive statistics here. The mean's about 500 for each. You have a little bit difference in standard deviation. And the correlation is 0.78. This will help us guide our data. You can see these data in Excel or in R. This is looking like a matrix. This is what we're going to define it as. And we'll use these data to describe the different operations in matrices as we go forward. So let's do some definitions, particularly where we're talking about what a matrix is and how that differentiates from a vector, and then what a scalar is. And turns out a scalar is just a number that we're used to using, but we'll put it in context with matrices in just a bit. So matrix is a rectangular array of data, right? It can be, typically matrices, let me back up a bit. Rectangular array, a box. That's what I like to say. It's used for storing numbers. We put our data inside the matrix itself. It's numeric. Matrices themselves can have unlimited dimensions. So you could have, like you think about, I keep calling it a box. A box, if you think about a box in life, it's three-dimensional, right? You put stuff in it. Well, that would be like rows and columns and something about the depth of the box as well. Like rows might be width, columns might be height, and then we need another set of depth. It could be thinking about collecting, think of this as collecting a set of variables across time, where at one given time point, there would be rows and columns of data, but there would be multiple sets of rows and columns making it three-dimensional. But for our purposes today, we're only going to stay with matrices that have two dimensions, right? Basically described by rows and by columns. Oftentimes, the matrix itself is symbolized with the bold-faced font and text, typically with capital letters. So capital X in bold represents a matrix. Matrices get described by the number of rows and the number of columns. So in this case, my SAT example, we had people down the rows. That's 1,000 people. So 1,000 rows and two variables. So that's two columns. And sometimes you see this denoted as, in parentheses, the size of the matrix, rows by columns. And typically we talk about rows coming first, columns coming second. So we would say the matrix X is of size 1,000 by 2. Now, size actually does play a big role in matrix products. If we're going to go make a multiplication of matrices, which we often do. So denoting how many rows and how many columns will become important. And that's why I'm trying to emphasize it here. But you can take a look at what we have. If you take our original data where we have people down the rows and the variables in the columns, that's just represented here in my box. We put brackets on the outside to denote the interior of it as well. So the very first column would be SAT verbal. The second column would be SAT math. The first row would be the first person's scores. Second row would be the second person's scores, etc. Now, a vector is a matrix where one of the dimensions is equal to size 1. So I guess in this case, more specifically, a two-dimensional matrix where one of those dimensions is size 1. So if we were to look at just SAT verbal, just this column right here of our matrix, that would represent what we would call a column vector, right? It will have 1,000 people, but it will have one column. So a 1,000 by 1 matrix would be sometimes called a column vector. Now, a vector often gets denoted with a lowercase symbol. So in this case, lowercase x, but it's still in bold, showing it's a matrix. And in my notation that you see here, the dot represents all of, basically substitute as all of. So x dot 1 means all of the people, all 1,000 rows, but the first column. That is how we would represent it. Similarly, a row vector is a matrix of size 1 by C. So if we took the first person's data, that would be x1 dot. So x for the first row and all of the columns. That would be a 1 by 2 matrix. And this here, you'd have just those person's scores for the first vector. Once again, the vectors are written in boldface text, often with lowercase letters. The dots represent the dimension aggregated across in the vector, the all of, as I was saying previously. Sometimes, and you'll see this in my notation as we go forward, rows and columns get separated by a comma, making it possible to read double digits in either dimension, right? So we may have to put a comma here if we get to the 400th or 500th cell or something along those lines. We'll see that in just a bit. So each matrix or vector, remember a vector is a matrix, but it's a matrix with one of the dimensions being size 1. Each one is composed of a set of elements. So the actual numbers in the matrix, one of those numbers is called an element. So for our matrix of data, capital X, which remember we have 1,000 rows and 2 columns, 1,000 people, 2 variables. Each element, each number, would be denoted by the letter X, and 2 subscripts, I and J. Now this X, you'll note, is not bold-faced. More on that on the next slide. But I and J represent the row position and the column position of that observation. So if I wanted the first person's SAT verbal score, it would be lowercase x 1, 1. Similarly, if I wanted the second person's SAT math score, it would be lowercase x 2, 2. Right? So each one of those numbers I'm replacing with a variable or an x here to represent what it could be in a matrix. And it turns out that single number is actually called a scalar. Now, before we just would call it the score or the data, but a scalar is what we call it for here in matrix world because it has an important geometric feature to it. And we're going to see that in a few slides as well. But what we can think about as a vector as being sort of like a line or emanating from an origin. And when we multiply that by a number, that line will grow or shrink. It sort of rescales. So the scalar in this term, in the matrix world, is something that sort of rescales a matrix or a vector, changes its length or changes its dimension. It's where the word scalar comes from. But scalars, again, are just numbers, and so we treat them just like a simple variable that we would see in what we would just have regular algebra, right? Our algebra 1 sequence that we would learn in elementary, middle, and high school, right? Or in college as well, if you were like me in college. But yes, scalars typically written without boldface, so just x, but the element position, row position, column position, x11 represents first person, first variable, SAT variable. So each element of a matrix is a scalar. Okay, let's talk about a few matrix operations here. First being the transpose. The matrix transpose, or the transpose of matrix, is a reorganization of the data, switching the indices for the rows and columns. So for instance, if X was 1,000 rows with 2 columns, each where our SAT verbal and SAT map are the columns and person 1 through person 1,000 are the rows, X transpose would be a 2 by 1,000 matrix, where now the first row represents SAT verbal, right? It was the first column before, and the second row represents SAT math. So basically, now the variables are the rows, and the people are the columns. So if the first person would be in the first column, and so forth. Now you're thinking, why would I want to do that with my data? This is something that happens in matrix algebra. We may need transposes to help us do certain types of operations, in particular matrix multiplication. We'll see why in just a moment. So matrix transpose is a simple operation where we just take a matrix, shift its size, basically rotate a box to its side. The data are all the same. We've just stored it in a different way. Right? So all the information is still there in the matrix. It's just displays differently. Now, each element in the matrix, right? If we had an element xij in our first matrix, in the second transpose matrix, it would be xji. We literally just swapped the row and the column in these matrices. And the way I denote matrix transpose is with a superscript t. That t represents transpose. I choose the letter t. Others will choose like a apostrophe, like prime. I stay away from that because that also has other meanings in mathematics, like derivatives. So x superscript t represents the transpose of the matrix X. It's not raising X to a power, but it is just a transpose, a reshifting of rows and columns. Now, there are also other definitions. We need to define a few matrices that we end up seeing a lot in statistics. First being a square matrix. If we're talking about a matrix being a box or being some type of rectangular object, a square has equal rows and columns, basically. Square matrix, same size in rows, same size in columns. And where we see this a lot are correlation or covariance matrices, distance matrices. These are all things where we will have equal numbers of rows, equal numbers of columns. Now, a diagonal matrix is a square matrix, right? So again, equal numbers of rows, equal numbers of columns. But the diagonal matrix is one where there are only numbers down the diagonal, and all elements off diagonal, right? Not down the middle of the diagonal of the square matrix. All of those matrices, all those elements are equal to 0. Right? If you want it mathematically, you could say when I equals j, right? When the row equals the column, the x value or the element is not equal to 0, right? So this thing right here. And for zeros the zeros in the off diagonal elements would be for I not equal to j, x equals 0, right? So when I is j, you're down the diagonal. When I equals j. When I does not equal j, you're in the off diagonal, and that's where we can set the zeros and the ones. That's the mathematics behind it, the symbolic nature of it. Now, we use symbolic matrices in statistics because it turns out we've talked a bit about covariance and a bit about correlation previously. But if you want to transform your data from one to the other, we use diagonal matrices. So a correlation matrix, if we want to turn it into a covariance matrix and we have the standard deviation for each observation, we could actually do a matrix product of diagonal matrices multiplying the correlation matrix in the middle, and we would end up with a covariance matrix. Similarly, we could transform from covariance back to correlation in the same way. A symmetric matrix, then, is also a square matrix, but that is what a square matrix where all elements are reflected across the diagonal. So if you remember the correlation matrix, we have, going way back in our slides, this is a square matrix. It's symmetric because the term above the diagonal is repeated the term below. There's reflected. We want to put that into symbolic thought. That means any element xij is equal to the element xji, xi being the row position and the column position above the diagonal, or in this case, and then flipped ji below. So correlation and covariance matrices are square, and they're symmetric. That's an important feature. Some matrix products, some matrix operations are defined only on square and symmetric matrices. So this is sort of definitions we need to have to move forward. All right, let's talk a little bit more about vectors. Why not? Both row and column vectors can be represented as lines on a Cartesian coordinate system, or a graph, if you will. So let's consider the vector 1, 2, and the vector 2, 3. So we'll call the vector A, 1, 2. You'll see it's boldface, lowercase, and B, 2, 3. These are both column vectors, although the orientation of row and column is less meaningful here. This is just by convention, I'm calling them column vectors. What we can think of vectors of doing is being a dot at those coordinates. So let's imagine we have a graph, a Cartesian graph here, and 1, 2. The very first element would be the value of the first dimension, or the x-axis, and the 2 would be the second element would be the value on the y dimension. So we put a dot there, right there. It was a graphing task. I remember doing this way back in elementary school. What we're talking about a vector being is a line that emanates, or that starts at the origin, starts at 0 in each dimension, and terminates at the dot where that value is stored. So if we think about it that way, this gives us a geometric representation of our numbers. Now, it's interesting, depending on the type of learner you are, geometric representations can either really enhance what you're doing or really confuse what you're doing. For us, let's just, if it confuses you, just bear with me and try not to think about when we start talking about statistics with this. But let's continue on a little bit here. Right? So the vector A starts at the origin, goes up to this dot. The vector B starts at the origin, goes up to the dot 2, 3. But when we see those lines, now we can start thinking about things, right? Which line is longer? Can we quantify the distance? Can we quantify its length? Are there multiple ways of quantifying its weight? Yeah, yes, we can do all of that. We can go even a step further, right? We could talk about what is the angle between these vectors, right? These are quantities that are important in statistics, or the statistical terms actually we use all the time, but they're actually describing each of those phenomena, right? Length and angular relation. But let's take a step back before we go too far. Think for a moment how we would plot our column vector, for example, with SAT Math and SAT Verbal. All right. Well, now quickly, instead of having 2 rows for a column, we have 1,000. So if we think about what that means, we need a 1,000-dimensional graph. And that's exactly right. We could think about our data as pointing into this, as being a line or in a 1,000-dimensional Cartesian coordinate system. That's crazy, right? That blows my mind a bit, but that's okay. That is what's happening. It's a way of thinking about it. So let's define vector length. Once we think of a vector as being a line, we can describe how long it happens to be. In fact, we can use the Pythagorean formula for this, right? Because if you think about this line, since it starts at the origin, if we were to go up either the first dimension or the second dimension and just make a triangle out of it, that line would represent the hypotenuse. And we know how to calculate that line based on the Pythagorean theorem. Right? So basically, if we took the squared value, the square root of the sum of the squared distances, we get that length. This is actually called a very specific distance. This is called the Euclidean distance. Right? There are other distances as well. One of the distances might be the sum of absolute values. Right? That is not what we're talking about here. But Euclidean distance is a very natural formulation. It does come from, again, Pythagoras and Pythagorean formula. It's pretty cool, pretty old, right? But we sometimes denote the length of a vector with these double bars along the vector on either side of the vector itself. So double bar x would be its length. Sometimes we just do capital L of x. Lots of ways of doing it. It all depends on the context of what you're reading. So from the last slide, the length of the vector A would be 1 squared plus 2 squared, or the square root of 5, right? Or 2.24. And the length of vector B would be the square root of 13, 3.61. So we can tell vector B is longer than vector A, which is exactly what we see with our eyes. And that's nice. Okay, great. We're describing length. In our data, the length of the SAT verbal is 15,868.138. And the length of SAT math is 15,964.42. Now, interestingly, the length of a vector is analogous to its standard deviation. By analogous, I mean related to, right? If we were to go and look at SAT verbal and we mean centered it, right? I didn't mean center it here, but if we mean centered SAT verbal, then the length is the square root of the sum of mean deviations, right? It's not quite the standard deviation, but it's very, very close. So you can think of that length as a proxy for how much variation you have. So now when we're thinking about our 1,000-dimensional space of our data, if we were thinking about these vectors, but for our data, how long that vector is describes how much variation that variable has in this crazy hyperspace of 1,000 dimensions of our data. But we can also define addition, right? Vector addition is something that we may end up wanting to do. We can add them together, create a new vector. Vector addition is done element-wise. So if we were to say we're going to create a new vector C, where we're going to add A plus B, then each element, the first element of A is added to the first element of B, and its sum represents the first element of C, right? So here, 1 plus 2 is 3, 2 plus 3 is 5. The new vector C has the coordinates 3, 5, right? So to do this, to add vectors, we must already know that the number of rows must match, right? And the number and the column also must match. So we're building toward matrix addition as well, but vector addition helps show us that. Now, what happens geometrically, I'm going to show on the next slide. But really what it shows is it creates a new vector along either of the previous two, right? So if we go here, here's A, here's B. If we add B to A, we end up at that point, or vice versa. If we add A to B, we end up at this point over here in space. And this new vector right there is really the sum of both of those. So we can see how this works geometrically. Now in data, a new variable, say SAT total, we might want to add SAT math and SAT verbal to get a total SAT. Maybe for college submissions, or who knows what it happens to be, what you might want to do for that. But that would simply be the first column vector plus the second column vector equals SAT total. Now let's talk about vector multiplication, but vector multiplication by a scalar. And this is where the term scalar shows up. When you take a vector d, let's imagine, or set a new vector d equal to 2, the number 2 times the scalar number 2 times the vector a from our previous set example. Remember, vector a was the value 1, 2. When we multiply a vector by a scalar, each of the elements are multiplied by that scalar. So 2 multiplies 1, giving us a 2 in the first element of the new vector. 2 multiplies 2, giving us a 4 in the second element, second row of the new vector. What scalar multiplication does is it changes the length of the vector. And the length of the vector d is 4.47, whereas the length of the vector a was 2.24. Literally, we have doubled the length. By when we multiply a vector by 2, we extend its length by 2. Similarly, if we were to multiply this by 0.2, it would be 20% of the length before it'll shrink or grow the vector. It basically resizes the vector. Now, we use scaling in other contexts in statistics as well. If you think about the coefficients of a linear model, they have their own scale of units of y per units of x. Or we might talk about putting people onto a scale, like a psychometric task. So that also has meaning, but it's not as literal as the idea that we're changing the length of a vector, rescaling it. Okay. And if you think about in a general linear model where you could see this, uh, the fixed effects, the slopes, the regression slopes, are scalars. And if we have our data, we're multiplying. If we think of let's imagine y equals beta 0 plus beta 1x. If we put y and x as matrices, then beta 1 is a scalar that rescales the vector x as we predict y with it. This is a representation of it geometrically, right? So if we have a vector v and a vector u, and we both multiply those by a scalar a, excuse the resolution on this slide, you can see that that scalar a was bigger than 1, it would lengthen or extend the length of both of those vectors. We could also talk about vector addition, right? So this is vector addition in the lower left. But if we had if we did both, right, we could see here, turns out multiplying by scalar, we can distribute the scalar quantity across a sum of vectors. So this is just like we would do with typical numbers. Here, we could see the scalar addition, scalar multiplication just lengthens the addition as well too. So that brings us to another important concept, the idea of linear combinations. We've talked about linear combinations in the context of linear models, saying that, oh, the predicted value on the right-hand side is a linear combination of regression coefficients times variables. Or we've also talked about it saying, what is our simple slope? Or what is the interaction term? Or how does the interaction change the main effect? Well, that's also a linear combination. Technically speaking, addition of a set of vectors, all multiplied by scalars, is called a linear combination. So we could create a new variable y by taking a linear combination of a scalar times a vector x. Right? So here, y itself is the linear combination. And for all k vectors, there are k x's here, the set of all possible linear combinations. So think of it this way. Here's a set of vectors of real numbers. Think of all the different possible a's that could be here. That is called the span of the vector. Now, we don't often think about that in most analyses, but sometimes we do. That span of the vectors, the vector space itself, that is a little bit more advanced matrix topic. But when we're in things that don't, when we work with things that don't exist, say latent variables, psychological constructs, that span becomes somewhat more important. Mainly because we can talk about changing its span, changing its basis for vectors as well. Where we do see this, where we see linear combinations a lot, are linear models. I mean, you can see the predicted value is a linear combination of regression coefficients times our predictors. And in this case, we don't have a constant in front, but we could add a constant. That would still be a linear combination. That would be the intercept. Also, there's a term that we're going to talk about a little bit later, something called principal components analysis, whereby we try to basically take linear combinations of our data to create new variables, such that the new variables are independent from each other, number one, and that they are ordered in the sense of how much maximum variation there is in our data. Now, that's a complicated topic that we're going to get to in just a bit as well. Okay, so let's go back to the linear combination. A set of vectors, we have to define something called linear dependencies, right? A linear dependency, or a set of vectors, are said to be linearly dependent if the sum of a linear combination is equal to 0 and all of the a's are not equal to 0, right? So let's take an example for this definition. Let's imagine we're forming SAT total, right? Where we have a 1 for SAT math, verbal, and a 1 for SAT math, multiplying each. So that's our scalar. We just sum those up. The new variable is actually linearly dependent with the others, right? So if we did a little algebra, let's say we subtract SAT total from one side, we can see now we have SAT math times 1, SAT verbal times 1, and then -1 times SAT total. If we do this math, we add these together, right? We get 0, right? Now this 0 is in boldface. That is something we call the 0 vector, right? But this is, by definition, a linear dependency, meaning uh, SAT verbal, SAT math, and then the total, which is comprised of the sum of those two, are linearly dependent. Linear dependencies is what we would define as oftentimes the upper endpoint of when we have variables that are multicollinear or highly correlated, right? What we're saying is when you have a set of variables that are linearly dependent in a matrix sense, those are not going to go well in your prediction. Potentially, if we want to go and predict an outcome, let's say we're predicting uh, first year freshman GPA in college, and we want to predict it by SAT verbal, SAT math, and SAT total, guess what? That's not going to work. We're not going to be able to do that prediction. Linear dependencies are bad for statistical analyses that involve matrix inverses. Technically speaking, well, we haven't defined a matrix inverse yet. When we get to that quantity, you'll see that this a linear dependency means the inverse cannot be found. All right, let's go a little bit further. There's something we're going to define as it's like a matrix product. It's called a dot product or inner product. And this right here, the how we define it, if we take A dot B, looks like A multiplying B. Similarly, this would also be formed by A transpose B. Now remember, the vector A and the vector B, these are column vectors. So by transposing A, it becomes a row vector. So we're starting to see how matrix multiplication works here. But it's a little bit simplified with our row and column vectors. But here, how it's formed is basically taking each element of A and multiplying by its respective element in B, and then summing the total up. So this is the sum of the elements of A times the elements of B. Now, you'd say, okay, great. That seems to be reasonable. Yes, it is absolutely reasonable. That's what we'd want it to be. It just looks a little bit different when we get to a matrix because we're going to have a lot more permutations of which rows of A and which rows of B in the matrix to work. But this is inner or dot product. This is specifically related to the angle between vectors. Or another way of putting it is the projection of one vector onto another. You can look at vectors in different ways that way, and we'll talk about projections just a bit too. So from our example, if we wanted the inner product of A and B, we'd see it's 1 times 2 and 2 times 3. That sum equals 8. Or in our data, we'd see it's quite a bit bigger. 251,928,400 is our inner product. Now, those numbers themselves don't really have much meaning, but we will provide meaning to those in just a bit. Where it actually does have meaning is the angle between vectors. So the result of the dot product, or actually a version of that, is related to the correlation between variables, right? And we can use that when we build what we call a projection of one vector onto another, or one vector onto a set of vectors. And that projection is really related to what we do in linear models. So the angle between vectors, as vectors, we can remember, we can think about that geometric representation, that two-dimensional graph of vector A and vector B. The angle between them is equal to the inverse cosine of the inner product of A and B divided by the length of A times the length of B. So the angle between vectors A and B happens to be 0.12. Now this is in, I believe, degrees. And then from our data, itself, if we were to look at the angle between SAT verbal and SAT math, it'd be 0.105. And right now that doesn't have much meaning, but we can actually see that the cosine of the angle between these two vectors is actually the correlation, right? So if you think about what we're doing here, right? Here's our angle AB. To get the angle, we need the cosine of A dot B over length of A times length of B. Let's go put that here. So before we go and take that inverse cosine, if we just take the term in the middle of it, right there, and we start plugging in numbers, what we're starting to see is a formula that will give us the same formula as the Pearson correlation. So really what we're saying is our angle between the vectors is a rescaled correlation. Pretty cool, I think. So our SAT example, we see the correlation is right about 0.78, 0.775. Let's define projections. A projection is just like you would think about from a projector screen or a way of looking at a shadow, for instance, right? A shadow, like when the sun, let's imagine you're standing in the sun and you look down, you see your shadow. Your shadow is your projection onto the space of the ground, but the sun, where the sun is not hitting the ground from your shadow itself. So you think of yourself as a vector and the rays of light as a vector. What's left over from that, casting the shadow, is its projection, right? So more specifically, the projection of a vector A onto B is an orthogonal projection of A onto the straight line defined by B. So imagine we have the vector B here, we have the vector A here. A projection would be, imagine shining a light on A straight down. What is the shadow A casts onto B? A way of thinking about that. That term right there, that new vector, we sometimes call A projection B, is formed by the dot product of A time A dot B over the squared length of B. And that whole quantity rescales B as a scalar. I mention this because you can actually represent linear models as a projection. Right, so let's imagine this. We have X1 SAT verbal, X2 SAT math. And I can only draw it in 3 dimensions, or we can only see it in 3 dimensions, but maybe 4 if we do some motion. But these are 1,000 dimension things. Let's imagine we have first year GPA is Y. Well, the predicted value of Y is the projection of Y, right, first year GPA, onto the space defined by SAT math and SAT verbal, right? And so this green box right here is sort of the column span of the vectors that we're doing for the prediction. So to me, this is cool. The length of the vector that goes between the prediction and the predicted value turns out to be our residual, related to our residual standard error. Right there. There it is. And this is an example with what we have as well. All right. Now we say all about vectors, because remember, vectors are matrices where one row or one column are set to 1. Let's put them into the context of matrices now. So a matrix can be thought of as a collection of vectors. So you could think of matrix operations are like vector operations. I say on steroids, it's a little bit colloquial. Lots and lots of vector operations. I'm thinking steroids in the sense of, you're trying to get swole. Matrices are swole vectors. Maybe that'll work. I don't know if that works. But anyway, lots and lots of vectors. Matrix algebra defines a set of operations and entities on matrices. And I'm going to present a version of what those operations are to try to mirror what you may have experienced in algebra. And this, for me, is what my memory of algebra happens to be. And as I get older, that memory fades. Although thankfully, I do work with a lot of math educators who are interested in making sure children learn algebra. So I have a little bit of a sense of how that works. Don't just rely on the old memory here. The definitions that we're going to come up with are, what is an identity matrix, right? Identity meaning the number 1 in a scalar sense. What is the zero vector? Well, we've already seen that before. What is a ones vector? Oh, wait, what's a ones vector? Well, it's just like it says. If a zero vector is a vector that has zeros through every element, a ones vector is a vector that has ones, but why it's important, you're going to find in just a bit. And then we're going to have matrix operations that we're going to define. Now, just a few quote unquote basic operations, addition and subtraction, multiplication. And then I put division in quotes. It's not quite division, but we can think of it that way. So I'm going to draw a parallel to what we do when we divide numbers as we go forward. Okay. So matrix addition and subtraction are much like vector addition and subtraction. The rule is, though, matrices can only be added together when they're the same size. This used to blow my head, where you're saying that I sometimes can't add numbers. You're right. Right. Matrices that are the same vector, or matrix addition is only defined on matrices the same size. That's a weird concept where it's like I can't just add all the numbers. Correct, because if you have a matrix that are differing sizes, it's representing a different geometry, and we're not quite sure how to add those together. But if you have the same number of rows, same number of columns, sum them together, you can add the matrix. You can create a new matrix. And the way we do that is just the same way we did with vectors. The new matrix is constructed by an element by element addition and subtraction of the previous matrices. The order of addition and subtraction does not matter, right? So you're like, of course it doesn't. So if I add 1 to 2 or I add 2 to 1, I both end up with 3. The same thing works with matrices, which is nice. Here's an example. We have the matrix A with all our elements, A1, 1 through A4, 2. The matrix B. Matrix A has 4 rows and 2 columns. Matrix B has 4 rows and 2 columns, meaning we can create the sum A plus B or the difference A minus B. When we create that sum, we just go element by element, right? The new element 1, 1 of our new matrix is the sum of element 1, 1 from A plus element 1, 1 from B, right? And we do that for all the elements. Same thing with subtraction, right? Subtraction is just like multiplying the matrix B by scalar -1, if you want to think of that, and then adding it to the matrix A. Same thing. Let's just say element 3, 2, pick one at random, is element 3, 2 of A minus element 3, 2 of B. Right? So it's pretty straightforward. I like that. If you try, by the way, if you have two matrices, let's say in a statistical package like R, and you try to sum them together, it will give you an error. Say this operation, matrices do not conform. Yeah, that's right. They need to be the same number of rows, same number of columns. Now, matrix multiplication gets a little bit more complicated. The new matrix, let's imagine we want a new matrix C, that's going to be the product of matrix A and matrix B, right? The new matrix C, it's not as simple as multiplying each of those elements together. What we're going to do is create a new matrix where the elements are the inner product of each row and column they represent, the vectors of that. So it gets a little complicated, but basically, we have to take a matrix, we have to sort of define a concept of pre-multiplying and post-multiplying. So in this case, if we're taking A times B, the pre-multiplying matrix is the one on the left, A, and the post-multiplying matrix is the one on the right, B. And the key part of this is the number of rows, or excuse me, columns of A has to be equal to the number of rows of B to form the new matrix C, to do the matrix multiplication. Right? So the number of columns of A must equal the number of rows of B. When that happens, the new matrix C actually is not the same size as either of the previous matrices. Right? What C's size does is it takes the rows of the pre-multiplying matrix, so in this case R, and it's the columns of the post-multiplying matrix, K. So C's size is R by K, even though A's size is R by C, and B's size is C by K. It's a little bit more complicated, like I warned. All right, so what happens to form this is we were literally going, if you think of our elements of C, let's take our first element of C. It represents the dot product between the first row vector of A and the column vector of B. Right. So that is literally taking a lot of information from A, a lot of information from B, condensing it and putting it into C. So because we have to have the pre-multiplying rows match the post-multiplying columns, the order of matrices matter, right? For instance, we can define the product of A and B, but we cannot define B times A, right? We cannot make B times A work because the number of columns of B does not equal the number of rows of A unless K and R are equal. Let's show it a little bit with some symbols. All right, let's say we want to take A times B. Let's imagine our matrix A is rows 4, columns 2, and our matrix B is rows 2 and columns 3. So first question, do the number of rows match the number of columns of A match the number of rows of B? The answer is yes. There are 2 columns of A, there are 2 rows of B. We're good, we can multiply them. Great. What is the size of our new matrix? It will be a 4-row by 3-column new matrix. Great, that's step 2. And if we want to go and figure out what it is, each element is, we have to think of how we're multiplying them, right? So here, the very first element A of our new matrix AB, takes the row vector, the first row vector of A1, 1, A2, 1, right here, this very first row, and does the dot product with the very first column vector of B. right? So that represents A11 times B11 plus A12 times B12. That gives us the sum. So this sum right here is our very first element. Likewise, the highlighted one in red, the first row, second column would take the first row's row vector and do the dot product with the second column of B, and we would end up getting the sum A11 times B12, A12 times B22. So all of this is pretty confusing, and all of this is where like matrix algebra starts to get hard. But this pattern is very regular, and it helps us do a lot of statistics in shorthand for a lot of what we end up having to do. And we're going to see that as we go forward. Actually, we're going to see that right now. Right? So, for instance, many of our statistical formulae could be re-expressed with matrices. A common matrix multiplication form is X transpose X. You see this in lots of places, right? So it's if you put our data in X, we take our transpose of X and multiply itself, then the diagonal elements actually represent the sum of the squared values of that vector. And the off-diagonal elements are the sum of the products. And I'm pretty sure you've seen enough statistical formula before to say that, oh, the sum of square things, that shows up in, let's say, standard deviation formulas. Oh, and the sum of products, that's like a covariance or correlation formula. You can see where we're going with this, right? This is actually the sum of squared terms here. So let's define the identity matrix. The identity matrix is a matrix that, when pre or post multiplied by another matrix, just results in that matrix itself, right? So if we take A as the pre-multiplier and the identity I as the post-multiplier, we get A back. Or similarly, if we take I as a pre-multiplier and we multiply A with it, we get A back. The identity matrix is simply a square matrix that has a square and diagonal matrix that has diagonal elements of 1 and off-diagonal elements of 0, right? So this diagonal right here of 1s is what does the work. What you will see is the size of it can be resized so that the matrix math works. Identities are just, we have to make a matrix product. We have to have the rows of the pre-multiplier match the columns of the post-multiplier. And so we just resize I to be the right size to build the matrix itself. The zero vector is simply a vector of zeros. And the key about the zero vector is when pre or post multiplied, the result turns out to be the zero vector. It sort of sends our matrix to null, to zeros, right? Just zeros everything out. So again, because this is just a concept that we use, we can resize this arbitrarily to fit a matrix product. So we can always make a matrix go to 0 by multiplying it by a zero vector of the right size. And it can be pre-multiplied here, or post-multiplied here, or pre-multiplied here. And similarly, the ones vector, this term, is a vector of ones. And again, we can resize it. It's just a boldface 1 usually. We can resize it to make it fit our matrix multiplication. But why ones is important is because, remember, when we do matrix multiplication, we're summing a series of dot products. And when we do a dot product of a vector with a set of ones, it simply becomes the sum of the first vector's elements. Well, we see this a lot. If we want the mean of one of our variables, sometimes we call that the mean vector. If we have more than one variable, we multiply each of our column vectors or do the dot product with the ones vector, and we get its sum. And we just have to divide by n as a scalar, and we get a mean. Okay, so we've talked about all that. Now we're within quote-unquote division. But to really call this division, let's really redefine what division is in algebra, right? If we think here, a divided by b, just in scalar algebra, that really is, we could re-express this as the quantity 1 over b times a. And sometimes we call 1 over b its inverse. So we do that b to the negative 1a. So if we redefine algebra that way, and we allow a divided by a to equal 1, then what we can see is in matrices, division plays a similar role. Now, I'm going to define this only for square and symmetric matrices. Only for that. But for square and symmetric matrices, an inverse matrix is a matrix that, when pre or post multiplied by another matrix, produces the identity, but with it itself, produces the identity. So similarly, A inverse times A should give us the identity matrix, right? So if you think back up here, A inverse times A in scalars would be A divided by A, which should give us 1, right? Similarly, A times A inverse also would give us the identity matrix. So again, if we're talking about square and symmetric matrices, square and symmetric matrices, A will have R rows and R columns, or basically the same number of rows, the same number of columns. The matrix inverse also will have the same number of rows and columns as the matrix itself, right? So we can do pre and post that itself, that sort of narrowing the definition of what an inverse is to square and symmetric matrices, at least for this class, simplifies us by saying basically any square or a square matrix, symmetric is square matrix, uh, can be a pre or a post multiple of itself, no problem. Its inverse has the same size, so it can be in pre or post multiple, and that makes the matrix math work out. Now, computationally, if we're going to use a computer to do this, the matrix calculation matrix inverse is quite complicated, right? And I say computers have a tough time. Well, they can arrive at a result, but the problem is it takes a lot of calculation. And every time we do a calculation in the computer, we have to worry about rounding error. There's only so many ways a floating point number represents a real number. A sort of error in each calculation. That is why there are a number of numerically stable techniques. So what I teach you or what you learn about matrix algebra, if you go a little bit further and want to do some development of statistical methods, what you learn in the textbook about matrix algebra changes a bit in how we actually calculate our computational side. It takes a little bit of thought as to what types of ways that we could go and do matrix or inverse or other terms where they're numerically stable. But that's just a thing to highlight. If you're not going to go write code or you're not going to build your own products or matrices, probably not your concern. The other thing that is your concern, though, is not all matrices can be inverted. What we will say is if a matrix cannot be inverted, it's called a singular matrix. And in statistics, we often see singular matrices when we're trying to take let's imagine we have a correlation matrix of variables that were linearly dependent. Remember, we made that definition before. Let's say we go and take SAT math, SAT verbal, SAT total, put them in a correlation matrix. If we try to invert that, it will not be able to be inverted. It's singular. Another way of thinking about it, when we talked about linear dependencies, those were multicollinear data, right? So high correlations among variables can turn out to give you a matrix that cannot be inverted. Now, the inverse itself shows up constantly in statistics. You may remember that first formula we had was X transpose X inverse when I showed that way at the beginning of this lecture. Here, where we typically find the matrix inverse is in models which assume some type of multivariate normality. We'll need an inverse covariance matrix. Like, all right, which models assume that? Almost all of them that we're working with. Even in a generalized linear model where your outcome may be not normal, you may have to take a matrix inverse of the predictor side, the X matrix itself. So let's see how that works. Remember, X transpose X, our data matrix was 1,000 by 2, so we're not inverting it. But if we look at X transpose X, right, that's 2 by 1,000 times 1,000 by 2, or a 2 by 2 matrix, which is square and symmetric right here. We can go and invert this matrix, and we'll see a bunch of very, very small numbers. And furthermore, if I then took the product of X transpose X times X transpose X inverse, we would end up with the identity matrix where there's ones in the diagonal and zeros in the off diagonal. So here's a bunch of algebraic properties of matrices. You'll see these are very similar to what we see in a lot of algebra with scalars. There are just a few subtle weird things that show up. One being like the matrix products A, B, the transpose of that is actually equal to the transpose of B times the transpose of A. If you take a matrix algebra class, you will either have to demonstrate this or probably read the proofs for each of these. That's not something we really need to think about. Come back to this if you need it. Okay, we're here finally to the part where we can talk about advanced matrix operations. So These are all related to multivariate statistical analyses. Sometimes might call this classical multivariate, a field of multivariate statistics that showed up a lot before maximum likelihood it took over. But to think about this, let's consider our correlation matrix of our SAT data, right? Well, one's in diagonal. Correlation of the off diagonal, it's square, it's symmetric, it's size 2 by 2. We'll call that the matrix R. So the matrix trace is a concept we end up using in statistics quite a bit. For a square matrix A with lowercase p rows and columns, remember a square matrix has same rows, same number of columns, same number of rows, same number of columns. The trace is the sum of the diagonal elements. So we just sum the diagonal right here. So sometimes known as the TR of A is the sum of all the diagonal elements. So for our data, the trace of the correlation matrix is 2. It's just the sum of the ones, the number of variables we have. In fact, for all correlation matrices, because the diagonal is a bunch of ones, the trace is equal to the number of variables because all diagonal elements are 1. And the trace is also considered the total variance in multivariate statistics. So when you think of your data, right, let's imagine we have SAT math, SAT verbal, and we have their covariance, but not the correlation matrix. What we're talking about is how much total variation is there across all the variables, not just the variable for SAT math, but both SAT math and SAT verbal simultaneously. That's the trace. And that trace, that total variance, is often used as the target to recover. Like when we think of a multivariate R squared, we would like to talk about how much of that total variance is explained by some type of model we're doing. That is where trace shows up. Likewise, there is another concept called a matrix determinant. Now, this only applies to a square matrix. Thankfully, a correlation matrix is square, but the determinant is characterized by a scalar. A square matrix can be characterized by a scalar value. That's called the determinant. Sometimes it's just single bars around the matrix, but sometimes it's just the letters DET. The determinant itself is not a length in the sense of the double bars around A. The calculation of the determinant is quite tedious. I'm not even going to show it to you here. You can go to your favorite AI tool and see how that works. But our determinant is 0.3916. But the determinant itself is very useful. Right? It shows up in very many multivariate statistical distributions. So for instance, the multivariate normal, which we'll talk about at the end of this lecture, uses the determinant in part of its distribution or PDF. But it's also a measure of generalized variance of multiple variables. So think of this as the area of this crazy geometric space where our variables are vectors pointing off into it. And if those vectors are pointing off into it with a very large angle between them, right, very widely apart, there's a lot of area in that space. Or if they're very narrow, there's a little area in that space. Right. Remember, the wide vector would say very uncorrelated data. The narrow, the vectors are very close together. Small angle would be very highly correlated data. And that highly correlated data has less general variance, less volume of that, what we call a hypercube in this space. So that's one concept. We will not focus on the generalized variances a whole lot here. It does show up occasionally, but the determinant is good for another reason. If the determinant is positive right here, the matrix is called positive definite, which means it has an inverse. If the determinant is not positive, the matrix is called non-positive definite, and the matrix does not have an inverse. So positive definite is what we want for most of our statistics. Non-positive definite is where our methods start to fail. The use of the term positive or non-positive makes me think of it's like corporate speak. I'm not positive about that, rather than I don't like that idea. That's the way of putting it. But positive means inverse. Now, there is another term if it's exactly 0, and when does that happen? But if it is exactly 0, we call that positive semi-definite, and that's semi-okay, depending on which method you're starting to use. Hope that helps. Okay, so now that's the end of the matrix part of the lecture. Much ado about matrices. They show up nearly anytime multivariate statistics are used, and they're often in help manual pages of the package you intend to use for analysis. And I put help in quotes there because if you're not familiar with matrices, you're not going to get a whole lot of help from it. Now, I'm not expecting you to do matrix algebra, particularly in this class, but I do want you to try to understand the concepts underlying those matrices. And I think because if you do, your working with multivariate statistics will be better. You'll understand a small amount of understanding about how matrices work will go a long way in how in how statistical methods work as well too. Well, I told you that thing to tell you this one. We are now going to talk about the multivariate normal distribution. It's our first multivariate distribution, very much like we talked about univariate distributions prior to getting into maximum likelihood. Turns out the PDF of a multivariate distribution can be used in a likelihood function as well too. And that's how we build multivariate statistics estimates using maximum likelihood. So multivariate normal is the one that we will focus on. There are other multivariate distributions. Those are less important now. So in this portion of the lecture, we'll talk about matrices and data and multivariate normal. We'll again use our data example from before where we have SAT math, SAT verbal. You can see the descriptive statistics here. And there's our matrices. All right, let's talk a little bit about distributions, right? Up to this part, we focus on the prediction or modeling of a single variable. We call that a conditional distribution or generalized linear model. But for us, multivariate statistics is exploring a joint distribution. Now, we can have a joint conditional distribution is really what we're trying to get to. This was a univariate conditional distribution. A joint distribution means two variables or more, right? And joint distributions really quantify how variables relate to each other simultaneously. So we have to adapt these conditional distributions to have multiple variables simultaneously, right? Later, we're going to see this as multiple outcomes, right? If you have more than one outcome of your study, rather than running separate linear models on each, we're going to combine that into one big joint analysis as well. And that gives us a benefit because we can then describe how much those two variables covary and how much our prediction may change that covariance between those two variables. So we will now look at distributions of two variables, right? Before we had f of x to define a PDF. Now we'll have, let's say, f of x1 and f of x2. If we put that in matrix form, we'll have f of x itself, where x, capital X in bold, is the size, number of observations by two variables, right? And the function here, so basically think of it this way. A PDF before, we would give it x, and we have to know, like, let's imagine we have a normal distribution. If we knew the mean and variance, if we give it a value x, like a score x, we get the height on that relative density curve. Now we give it more than one x, but we still get the height, right? It's defining this multidimensional curve itself. For two dimensions, we can actually visualize it, and we will in this slide or two. Now we're going to start with two dimensions, but we can move into many, many dimensions. And that's where, again, the geometric representation starts to break down. But that's okay. Just remember, multiple pieces of data in, one likelihood out. That's the key. So we're going to start, though, by describing descriptive statistics, multivariate descriptive statistics, basically mean vectors and covariance matrices, because the multivariate normal PDF depends upon these. A mean vector, which is a vector of all the means of the data, of all the variables you have, and the covariance matrix you're already familiar with, right? So in this lecture, we're only going to consider the joint distributions of sets of variables, but next time we're going to put this into a GLM-like setup where the joint distribution will be conditional on others. Basically, we're predicting more than one variable. So starting here, let's start with the mean vector. The mean vector is literally just a vector of each of the means of your data, right? So in our data, we could just look at our means, put them in a box. Right here, that's the mean of SAT math, the mean of SAT verbal. Here in matrix algebra world, though, it's 1 over n, which is a scalar, times our original data matrix X transpose times the ones vector. Now that ones vector is used because remember, each of the elements of X, to do this, we have a X is, let's say, n per people by P variables. The ones vector would be P times 1. So each of the elements of this mean vector would be the dot product of a variable with 1, which is simply the sum of those observations. And then we divide that by n. So there we have it. In R, we could do this as well. Here's some R script. Here, the term matrix develops a ones matrix in R right here. And to do a matrix product in R, we don't use the multiplier, the star, right? That's for scalars. We have to take our star and embed it in percent symbols. So X is a matrix. Ones is a vector. Well, it's a vector of length one, and X bar is now a matrix as well. Now, the mean vector is the center of the distributions of both variables, so SAT math and SAT verbal. Here, you can think of that if we were to look at these data and try to balance them, if they were physical quantities all weighing the same amount, this would be the fulcrum where we could try to balance that point on. Again, a graphic or a geometrical, a physical distinction of what this happens to be. There you go. There's the mean vector, right? The covariance matrix is a measure of the relatedness of variables. One of the covariances, we've talked about it before, it's sort of unitful correlations. It's expressed as the product of the units of the two variables. So here it's the sum of x minus its mean, x1 minus its mean times x2 minus its mean across all observations divided by n. Now, I will note that divide by n is the maximum likelihood version. The unbiased is n minus 1. We're going to see divide by n here in a lot of what we do because we're going to use maximum likelihood for what we do. Now, because units of covariance are difficult to understand, we more commonly describe association with a correlation, right? And turns out if we want to get a correlation matrix, we could just take this covariance and divide it by the product of each variable's standard deviation, right? So a correlation is the covariance divided by the product of standard deviations, this being the variance in the square root here. We like that. We could actually form the covariance matrix using a matrix product. X minus the ones vectors times the mean vector transposed. And you can see why we're starting to do this. We have to do the right type of dimensionality. We use transpose to sort of build a matrix strategically. And we know that we want a matrix where it's x minus its mean times x minus its mean, right? When we get this formula here. And that's how we may express it in matrices. I don't expect you to memorize this or to see it, but just describing how that works. So here what we can see is we can calculate that with our data. We can also do that in R as well. Now, if we want to go from covariance to correlation, it turns out if we take the diagonal of this, remember the diagonal of a covariance matrix is the variance. We make a diagonal matrix just out of that, and we take its inverse. What we end up getting is our, we need the square root of the diagonal here. The square root is the standard deviation. So we make a diagonal matrix of just the square roots of standard deviations, and we take its inverse, which an inverse of a diagonal matrix just takes 1 over each of the diagonal terms. So we do that, multiply it by a covariance matrix, and we get our correlation matrix out of it. All right, so we can show how this works. Here's our covariance matrix. The diagonal matrix D was the square root of the diagonal matrix here, which are standard deviations. So if we pre and post multiply that by its inverse, and again, that's just 1 over that for only diagonal matrices, this is true, then we get our correlation matrix. So again, we can do this matrix multiplication. And we can see that in R as well, too. Okay, I mentioned before the determinant is the generalized sample variance, right? It's sort of the measure of spread across all variables. Right? It really quantifies the area of a hypercube pointing off in that three-dimensional space. It reflects how much overlap in variables occurs in the sample. The amount of overlap reduces the generalized sample variance, right? So for instance, we know our correlation between our vectors, or correlation between our variables, SAT math and SAT verbal, is 0.78. So our determinant of the covariance matrix was 6,514,104.5. But if we actually had zero correlation, it'd be much larger. It'd be 16 million. Right? That's reflecting that. Remember that correlation is an indirect measure of the angle between the vectors. And the wider that angle, right? If we have zero correlation, it's like having vectors that are perpendicular, the biggest angle that we can get almost. That turns out to be wider variance of this hypercube that's defined by those vectors. So the generalized sample variance is largest when the variables are uncorrelated. It's also zero when the variables form a linear dependency, right? Remember, a linear dependency is like the vector angle becoming zero. And so the generalized sample variance goes to zero when that happens, right? The generalized variance is seldom used, though, but it shows up in the distribution function. So I'm really talking about it for that purpose. We could also look at the total sample variance. Here, the total sample variance is the sum of the variances, it's 90.67. It does not take into consideration the correlation among the variables. It will not equal zero if a linear dependency exists. This is only used in basically if we're talking about principal components analysis, how much variance each component might account for. That's where this shows up. Okay, let's get into multivariate distributions. For variables greater than or equal to 2, here, the multivariate normal distribution, it's a thing of beauty, even if it looks ugly to you. Let me just say it is the engine that drives most of what we do in a lot of statistics. The multivariate normal is the generalization of the univariate normal to multiple variables, right? And what I'm going to show is a bivariate normal as we go forward, because a bivariate normal is basically saying we have two variables, x1 and x2, and they are both normally distributed, but they're jointly multivariate normal. And so what the multivariate normal distribution does, or the distribution, the PDF, it takes all of our observations for a person and gives us the relative likelihood, the height of the density at that point. Now, because we have more than one dimension of variables, it's not a curve, it's like the height of the surface at that point. And the density function for it is given by this ugly term, right? So we send it a bunch of data for a single observation, and it puts that data into this here. It's where XP is. But the terms itself involve a determinant. Sigma is a covariance matrix. Mu is a mean vector. Right? So here's the determinant of sigma. And here's the inverse of sigma. So what you know is when I say you cannot invert, or if you have a determinant being 0, you can't get a matrix inverse. Well, if we have a linearly dependent set of variables, if we have multicollinearity, we know that determinant will be 0. Well, we can't divide by 0. That's a problem. So we can't build that multivariate normal out of it. Similarly, we can't invert that matrix. We can't even find the term of the product in the exponent here. But if you wanted to, and I'll show where all these terms come from in a couple slides here. All right, so going back into this, here's a PDF of the multivariate normal. The mean vector is given by just a vector, a column vector of all of our variable means. Our covariance matrix is a matrix that's square and symmetric. Again, the diagonal are the variances, the off diagonal are the covariances. This is why covariance shows up in a lot of statistics, multivariate statistics, and not correlation, because it comes from this multivariate normal density. In fact, in a lot of multivariate normal statistical methods, we're trying to figure out what the covariance matrix and mean vector happens to be using maximum likelihood or Bayesian methods. Now, we can compare the univariate and multivariate to see where we got to, where we get the multivariate from. So let's remember our univariate normal distribution here, right? X minus its mean squared over 2 sigma squared. We just do a little algebra with it, right? Let's go and take the normalizing constant. And remember that the square root is really like taking this term and raising it to a power of 1/2. Well, that's good. We can do that. The sigma there, turns out the determinant of a 1-by-1 matrix is just the number. It's a scalar. So I'm going to put in the bars to show that, oh, that's the determinant of a sigma squared raised to the 1/2 power. And then the exponent, let's just do a little bit more algebra. Let's take sigma and move it to the numerator. Well, that means we really need negative 1 over the reciprocal of its squared term right here. And pre-multiply it by x minus mu and post-multiply it by x minus mu. We can separate that algebraically, and it means the same thing. And now you can start to see where each of these components goes in our matrix algebra, in our multivariate normal, right? Here, the covariance matrix is determinant raised to the 1/2 power. That is similar. Now we actually have multiple variables, so that's where the v over 2 shows up here, and we get our term in the exponent as well. The key in all this is if we only have one variable, our multivariate normal distribution is a univariate normal distribution. So that's nice to know. Now, the term in the exponent right here, x minus the mean vector, the vector x minus the mean vector mu transpose times the matrix in its covariant inverse covariance matrix times the data vector minus its mean. That term, without the negative 1/2, is sometimes called the squared Mahalanobis distance. Now, that's a cool name. I like it. I almost thought about naming children after that. Unfortunately, probably going to get vetoed, so I didn't even suggest it. But maybe for your consideration, or maybe a plant, maybe a dog. I don't know. It's a great name. Sometimes we call this a statistical distance, right? It describes how far an observation is from its mean vector, but it's standardized by the covariance matrix. So basically standard units away. So it's like a multivariate z-score, right? And it turns out if your data do follow multivariate normal distribution, this term follows a chi-square distribution. So there's all these nice properties that show up. We actually use that. If we ever want to assess whether data follow a multivariate normal, we can actually use this and compare it to a chi-square distribution. Because if the data are multivariate normal, this should be chi-square. So oftentimes we denote a multivariate normal distribution with the number of dimensions it shows up. Now, I would say this often goes away in advanced statistics where everything's multivariate, but for our purposes, we can do that here. So our SAT example would have 2 dimensions, right? SAT math, SAT verbal. We'd show that. And basically, the multivariate normal shows up everywhere, right? It's in linear models, it's in linear mixed models, where it's in factor analysis, structural equation models, path analysis, exploratory factor analysis. We use it in multiple imputation. Basically, anywhere we would use a univariate normal, the multivariate normal takes that and puts multiple variables into place, right? I would say that the world revolves around multivariate normal distributions, and it really is the key to understanding many statistical methods. So here's a plot of a bivariate normal, right? This is a surface plot, right? We'd have one variable x1, we have another variable x2, and the density, the height of it is given by the PDF, right? So if you take any one point, take 0, 0, and you go up and submit that to the normal PDF, you end up getting the height. Now, if I go to the right, if I flew above this and made equal lines of equal height, this is like a contour plot, you can see how that looks. Now, I will note this is a multivariate normal distribution with a covariance matrix where there's 1s in the diagonal and 0s in the off diagonal. So it's a correlation matrix where the variables are uncorrelated. And sure enough, if you were to sample data from a distribution like this, if we would take random draws from this density, we get a scatter plot that sort of fit these circles, right? We'd have an uncorrelated scatter plot. The mean vector 0, 0 is also the height where the maximum of the density happens to be, the most relative, the highest part of the curve as well. Now, here's that same distribution, but with a correlation of 0.5, and you can see that distribution, that if we were to look at data, it's elliptical in shape. And in other multivariate texts, in classical multivariable texts, we could actually describe sort of what the angle is here. We could talk about coming up with multivariate confidence intervals from it as well. I'm not going to go into that much because I haven't found those to be very useful, but you could do that. And if you'd like to do that, I would refer you to some older multivariate books describing. But here, what I'm trying to tie this to is the multivariate normal. You can think about looking at a scatter plot of your data. The linear line would go kind of right through the middle of the XY line, and then you'd have your data scattered around that. And the higher that correlation gets, the longer these ellipses tend to be. And that correlation becomes 1. First of all, our covariance matrix is now singular, right? We can't invert it, but we would see the points fall on a straight line. Now, here's why we use the multivariate normal distribution. There's some really good properties of it. Linear combinations. So if a set of data, X, a set of variables X in a matrix X are multivariate normal, then all linear combinations of X are also normally distributed. So if you take a sum of variables weighted by some constant, it's multivariate, it's normal. Think of that. We use that in predicting in linear models. All subsets of X, so X1 and X2 out of X, although X5, those are also multivariate normally distributed. We can also show that a 0 covariance between pairs of variables at X implies that the variables are independent. It's not always true in more complicated distributions, but it is true here in multivariate normal. And finally, conditional distributions of X are also multivariate normals. So these are the features that we do to talk about what our data look like when we use, let's say, a path analysis or a structural equation model. Right? So to demonstrate how this works, we will go and take our mean vector and our covariance matrix, and I'm going to just plug in a few values and get their heights, right? So here with this mean vector, with this covariance matrix, if I took observation 631 who had a SAT verbal of 590 and SAT math of 730, the height of the curve for that one observation would be 0.139, et cetera, with a bunch of zeros in front of it. And then for 717, you would see a similar number as well, right? Now, if we plug in the mean itself, we get the highest number right here, 9924598. So that is the highest likelihood itself. And what you'll see is, okay, which one is more likely, relatively speaking? Well, it's more likely to observe the mean, of course, that's at the peak. But between the two observations I had pulled, it looks like, oh, 717 is. Well, those scores are a little bit below average. That's true, but they're also very similar in magnitude. Remember that correlation of 0.78 is where the density of the curve happens to be, right? So what we're doing here is we're pulling an observation that's closer to the center of the curve compared to the other one, where here we had a 590 for verbal, but 730 for math. That's like taking an observation close to the center on one dimension, so like right about here, but very far out on another, right? Whereas the other observation was about equally close to the center. So the distance between the two drives the height of that normal distribution. Now, what we're going to do going forward is estimate multivariate linear models in a structural equation modeling framework, use the package R, although that's not going to be in this lecture. So that's the multivariate normal distribution, an introduction to it. I wouldn't say it was a gentle introduction, but I'm not going to go and make you do anything more than just trying to understand what it seems like. You're welcome to go and take a look at the R code that accompanies the syntax to try to play around with the numbers. That does help for some people, not always, it does. Now, many of the concepts that we're going to see going forward of univariate models will carry forward, like maximum likelihood or model building via nested models, but all of the concepts do involve more multivariate distributions. So this lecture sets the stage to discuss multivariate statistical methods that use maximum likelihood. Matrix algebra was necessary to concisely talk about our distributions, which are soon going to become our statistical models. And the multivariate normal distribution is really used in almost every place that we see going forward, and it's really important to understand for that matter. So thank you for listening, and I will hope to talk to you soon.